You want to know what actually separates a textbook student from a top-tier Wall Street quant making high-stakes decisions? Well, you're in the right place. Welcome to a masterclass on how professionals actually isolate the signal from the noise. In this explainer, we're going to break down the absolute core of financial modeling.
Let's immediately shatter an illusion right here. Can one single variable, say interest rates or inflation, accurately predict the movement of an entire market? That works in Economics 101. But in global finance, a simple one-factor linear regression is just woefully inadequate.
In the real world, the answer is a definitive no. Uncovering the true drivers of a market requires us to untangle a massively complex web. Variables just don't act in a vacuum. Currencies, commodities, equities, they're all pushing and pulling against each other at the exact same time.
Section 1. The complexity of markets. To navigate all this complexity, professionals don't guess. They rely on heavy math. Think of simple linear regression like driving a fast car while looking through a tiny drinking straw. You're trying to use just one variable to explain a highly complex reality. Multiple linear regression, on the other hand, opens up the entire windshield. It lets us test theories, forecast cash flows, and extract exact dollar values by factoring in multiple underlying influences all at once.
Section 2. Anatomy of the equation.
Before we apply this to the stock market, let's deconstruct how this actually works using a high-end real estate market analogy. Here, we're estimating monthly rent per square foot. Our intercept is $44.67. That's our baseline, assuming all other variables are zero. Then, we introduce our independent variables, the property's age, its distance to the nearest metro, and nearby restaurants. Every single one of these slope coefficients tells a part of the story.
Take a look at that specific partial slope coefficient of 1.29 for the restaurant variable. What does that mean? It means for every single additional restaurant within walking distance, monthly rent increases by $1.29. But here is the absolutely crucial part. This is only true assuming the property's age and metro distance are held perfectly constant. That is the superpower of multiple regression. You're freezing time and space to measure one single impact.
Section 3. Isolating the signal.
Now let's pivot this intuition directly into quantitative equity research. We're looking at the famous Arnott and Asnes model, which forecasts the S&P 500's real earnings growth over a 10-year horizon. Our dependent variable is future earnings growth, and our independent variables, the trailing dividend payout ratio and the slope of the yield curve. We are essentially freezing macroeconomic noise to isolate these specific drivers.
The crucial data point here is that payout ratio coefficient of 0.25. In plain English, if the dividend payout ratio increases by 1%, we expect the subsequent 10-year earnings growth to jump by 0.25%. But remember the golden rule. This assumes the yield curve is held strictly constant. You isolate the variable to understand its true power.
But listen, this analytical weapon only works if your underlying data plays by 5 strict rules. The relationship has to be linear. The residuals must be normally distributed. The variance of the error terms has to be constant, a really critical concept we call homoscedasticity. Residuals must be independent, and lastly, you cannot have exact linear relationships between your independent variables. Violate these, your model isn't just wrong, it's dangerously misleading.
Section 4. When models break down.
In the real world, bad data and blown assumptions lead directly to blown-up portfolios. The first trap you'll face is model misspecification. This happens when you omit crucial variables, pool data from completely different economic regimes, or fail to transform your variables. For instance, if you use raw market cap instead of the natural log of market cap, you've misspecified the model because the relationship to returns simply isn't linear. Your inputs might be right, but your geometry? Fundamentally flawed.
Trap number 2 is multicollinearity. This happens when 2 or more of your independent variables are highly correlated with each other. Why is this fatal? Because highly correlated inputs create a totally false sense of confidence. They inflate your standard errors and render your slope estimates wildly imprecise and completely unreliable. You basically have 2 variables fighting to explain the exact same variance.
The third trap is serial correlation, which is incredibly common in financial time series data. This occurs when the residual for one observation correlates with the next. Positive serial correlation is a silent killer for quantitative strategies. It artificially shrinks your standard errors, causing your t-statistics to look massive. It tricks you into thinking you found a real edge, which leads directly to making disastrous type 1 trading errors.
Top analysts don't panic when they see serial correlation, though. They fight back. First, they detect it using the Bruce-Godfrey test, which accommodates serial correlation at multiple lags. Then, they fix it. They calculate heteroscedasticity-consistent Newey-West robust standard errors, recalculating their t-statistics to reflect the actual, true risk.
Section 5. The real-world application.
Understanding these deep mechanics is what truly separates a textbook student from a Wall Street quant. Instead of just looking at standard t-tests, modern analysts rely heavily on p-values to definitively evaluate if a variable actually moves the needle or if it's just noise. If your p-value is less than your significance level, you reject the null hypothesis. You've found a signal. If it's greater, you can't reject it. You have to be absolutely ruthless with your own data.
Section 6. The final verdict.
Ultimately, multiple regression is about responsibility just as much as it is about mathematical power. The model is literally only as intelligent as the analyst who builds it. It gives you the almost godlike power to hold the entire world constant just to test a single idea. But that power is completely conditional. You must meticulously check for homoscedasticity, root out multicollinearity, and aggressively adjust for serial correlation.
The math is pristine on paper, but the real edge, that lies in knowing exactly what to do when the data fights back. So, as you look at your next financial model, ask yourself, will it actually survive contact with the real world, or is it just a beautiful equation built on a foundation of broken assumptions? Think critically about the web you're untangling. Thanks so much for joining me on this explainer.